Hello and welcome to my channel. This is a quick video about how to calibrate the Nano VNA vector network analyzer. These are open source devices which cost thousands of times less than the original vector network analyzers, which were in a rack, and as tall as me almost. This is a nice instrument. Of course, you don't get the accuracy you get when you spend the price of your house on a VNA, but for the tiny money that they cost, they're an amazing tool. But you have to calibrate them, and for every frequency range you set, you have to calibrate in order to get accurate results. And what I've done is I've connected two cables. Sorry it's a bit dark, but it has to be dark so you can see the screen. The two terminations here are port 1 and port 2, and there are two cables connected. They're semi-rigid coax, which is fairly low loss and of reasonably good quality. They're 15 centimeters long. They're actually supplied with the analyzer. And on the end, most of what I'm doing is on port 1. On the end I've got an adapter back to back, because when you make the through calibration you have to connect it through to the other port, so you need to screw that onto here. With the device you get delivered, if it's any good, these calibration tools. That's an open circuit, a short circuit, and a 50 ohm matched load, which I'm going to need in a few minutes. So before you do anything, you need to calibrate it. And I want to test 868 MHz ISM filters over a fairly wide range, so I can see the bandpass filter characteristic, also measure the insertion loss at the center frequency, and measure the suppression a long way away from the center frequency, the attenuation of unwanted signals. So what you need to do is to calibrate this device. I've already set it up so that the S11 channel is in yellow, and that's in 10 dB per division. S11 is reflection loss, which you can convert directly to SWR if you want to talk in terms of SWR. So the lower on the screen the reflection loss is, the better the match. And the other channel, the blue one, is S21. That's the transmission from port 1 to port 2. And I've set this to be 1 dB per division, so that we may see a little ripple in the pass band or any ripple in the coaxial cables, because 1 dB per division is quite a lot of magnification. And both of these channels are set to log mag, so I want the log of the magnitude. I don't want a linear scale, because in dBs everything is logarithmic. So to calibrate, you just touch on the screen on the right and set frequencies. So what I'm going to do is I'm going to set a center frequency of 869 megahertz, because that's close to the frequency used for Meshtastic and Reticulum. So that was 869 M for megahertz. That's the center frequency set, hopefully. Then click here again and set the span, and I want the frequency span to be 100 megahertz. That's from one edge of the screen on the left to the edge of the screen on the right is 100 megahertz. Center frequency is 869. It's hard to see this. You wouldn't believe the setup I've got here with black t-shirts hanging over the camera to stop reflections from the ceiling and everything else. Sorry it's dark, but then if you make it lighter you can't see the screen. So it's 869 megahertz in the center, span of 100, S11, S21, that all looks good. So now we can do the calibration. So you just follow the instructions on the screen, which are a little bit cryptic, but how do we do calibration? Go back, cal, and then you have to hit the button that says calibrate, because I want to calibrate this first. And the first thing it wants in the list is an open circuit, and you can actually get an open circuit SMA connector. You have to make sure it's the right one. This is a tiny SMA plug which has nothing inside, there's no pin, so it's an open circuit. So you put that on the end of the cable. You don't put it directly on the device, because you want to calibrate this device for what appears at the end of the cable you're going to be using when you make the measurements. It's very important for phase, although we're not actually going to look at phase. Which reminds me, I've turned off the Smith chart display. I see a lot of people using these VNAs with extremely confusing displays because they've got the Smith chart visible as well, which we don't need for testing filters, and I think it probably confuses more than adds information, unless you're making matching networks. So I put the open circuit on, so now I press the button marked open, and it makes a sweep, and it's done. The tick in the checkbox shows that it's done the open calibration. Now it wants a short circuit. So I take off the open. You must make sure you get the right ones here, otherwise this goes very wrong. So I'm looking in the plug to make sure this really is the short circuit plug, and it has a small pin in the center to make a real short circuit. If I move the cable, you can see that's on there now. That's the short circuit plug. So we press short for short circuit. The very reassuring beeps. So that's done as a check mark. Now it wants a load, matched load. So I'm going to connect that, which is just a 50 ohm resistor inside a plug, but it's designed to provide a matched load up to several gigahertz, hopefully, although this is low-cost Chinese technology, so it won't be the best. Anyway, there's the load, and click the button that says load. So that's calibrated. oh yeah, okay, S11 is yellow, that's why. So the load is saying it's got a return loss flat against frequency of about 28 dBs, which is a pretty good match. As I said, the lower the line is for return loss, the better the match, but 28 dBs is very acceptable. Now it wants a through connection. That's where we have to connect port 1 to port 2 using the test cables that are going to be used in the measurements. And I'm going to have to bend this cable and plug the other cable onto the end here to port 2, so I'll do that outside. Screenshot. Probably the VNA will move now on the desk. These semi-rigid cables are quite stiff and you have to be careful not to bend them too much to avoid damage. So now I've got the through connected, and I'm going to press the button that says through to tell it that it's there. So that's finished. Now you can press the button that says done, because we're done calibrating. And then it invites you to save the calibration results in a channel, and I'm going to save it in channel 0. And later on I'm going to use software to remote access this device, and it likes to have things in channel 0, as far as I know. And as you can see, the span is there of 819 to 919 megahertz, because I said I wanted a 100 megahertz span. So we press save into channel 0, and that's now saved. So I've got the through connected, so you can see the insertion loss in the cables, which must be 0 because it's been calibrated for those cables, so that the loss in those cables is taken out of what you see when I put a filter there. So there's a flat line at 0 dBs, 0 insertion loss, and here's the matching. We've got a return loss of minus 50 dBs at the best frequency. The marker has found it. Marker 1 is at 850 megahertz. So that's where the best match occurs. That's port 1 looking at port 2 to see how well it's matched through the cables, and with the calibration applied on top. So that VNA is now calibrated and ready to use. And what I'm going to do is I'm going to make another video where I put various 868 megahertz bandpass filters in there and compare the results. And for that I'll be using the computer screen capture version. You can't use that for calibration easily, which is why I've done the calibration live on the screen of the VNA itself. That's what they recommend you do when you look at the software, as you'll see in my other video. So thank you for watching. Remember to like and subscribe and ask questions, and I'll see you in the next one.